Okay, so the topic for today discussion is partition function, and the partition function is represented by symbol z, and the z is taken from the German word which is Zustand, which means sum over all state. Stand means state and summa means sum over. So from we already know that from Maxwell-Boltzmann distribution, that the distribution function or the population of particle in different energy levels is given by the formula, and in this particular formula the denominator represent the partition function, and this partition function is given by z is equal to summation gi e raised ei over kt. This partition function shows that the partition function here gi represent the energy states and ei different energy level, where k is Boltzmann constant. So the partition function is directly a function of temperature. So it totally depends on temperature. Sum over all state, or the meaning of partition function, means that how an assembly of n number of particles spread over or can be distributed in the thermally available energy states or energy levels. Now depending on or considering this particular function of temperature, we have two conditions with respect to temperature. Now if we have a very low temperature, that is the temperature is approaching 0, at this low temperature the energy spacing between different energy levels are very high, or the energy levels are very far from each other. So in this particular case, when we have T is very low, as T is approaching 0, so the spacing between different energy levels, they are very far from each other, and at this particular condition we are just taking the Boltzmann vector, that is from the partition function gi e raised minus ei over kt. So we are just taking this Boltzmann vector e raised minus ei over kt. So from this we can explain everything very well. So you can look here, this k is constant, and this is something like directly proportional to e raised minus 1 over t. So just suppose we take this temperature very low as 0.02 Kelvin and put in this value. So e raised minus 1 over 0.02. So we are getting a value that is very small after calculation. It is 1.98 and 10 raised minus 23. So this is quite smaller value. Now if you take the temperature, choose a temperature that is a little bit higher, that is 200 Kelvin, and we just put in the term, that is minus 1 over t term, and it is minus 1 over 200. After calculation we are getting a value 0.998, that is approximately equal to 1. So from this you can see that if we are choosing a very low temperature, so the term is going to 2, and if you are toward 1. So when the temperature is very low, just explaining further, the temperature is very low, that is approaching 0. So we have this term, the exponential term in this minus 1 over t. So you can see here that we are taking the exponential term, just separating that 1 over 0 is mathematically is equal to infinity, and if you are taking the just putting the value in the above minus 1 over t, so e raised, if we put here plus infinity, so this is very high value, but we have here a negative sign, so minus infinity, this is quite a very small value, or very small value, that is very low, and this is approaching 0. So this value is giving us 0. Now if we open our summation term, that is z is actually a summation of gi e raised minus ei over kt. So this is the summation, opening the summation. So we can write down, for starting from ground state, g naught e raised minus e naught plus g1 e raised minus e1, and this is over kt plus g2 e raised minus e2 over kt, and this is so on going. So now just putting the value that z is equal to, for g naught is g naught, and here we have to put the value for e naught. We just put the value, this is ground state 0, and if you put here value 0, and down is temperature. So their temperature has some number, and this is other is constant, and plus here we write down 1, and e raised minus e1. This is some energy value, not 0, and down is temperature. So if we have temperature very, very low, and if you write down here in this, just not going further, so this is a representative term, and this is here just 0, just keep an eye over here. So if you divide 0 by any temperature, so from that we are getting automatically a 0, and this term, this will be 0, and this term will go to 1. So from this first term we are getting g naught multiplied by 1, so 1 plus. But what about other terms? Because here if you put temperature very, very low, that is 1 over some very low term, that is 0, 1 over 0, and this, from this we are getting infinity. So from this we are getting infinity, and if we have e raised minus infinity, as we already discussed here, that if we have e raised minus infinity, so that is giving us a very low number, and it is corresponding to 0. So here we will automatically get 0 from this. So all the remaining term will give us 0. So we have only this term remaining, because here is 1, and all the other term they are giving us 0. So at very low temperature, conclusion is that if we have T approaching 0, so our partition function correspond to ground state only. So this shows that if we have temperature very, very low, so only ground energy levels are available for the particles, and all other higher energy levels will not be available, because the energy spacing are very far from each other. Now just considering that if we have temperature very, very high, so what will happen? In that case, if temperature is very, very high, at high temperature the energy spacing between different energy levels are very close to each other, that is, they are very close to each other, and in that particular case we already proved that this exponential term in which we put temperature a little higher, we are getting 1, and just opening this summation term, just putting the value for the ground state, higher energy state, and so on. So just here is the ground state, so we put the energy value 0, and 0, if you are putting 0, and the temperature is, just keep in mind, this is very high, approaching infinity. So if you put here energy value 0, and down is infinity, so e raised 0 is giving us 1. Now in other case, if we have higher temperature, this is again giving us some value, that is some number by infinity. So if we have some number and we are dividing by infinity, so that is giving us a 0. So in this case we are getting this level is 0 and other level also 0, that is some number divided by infinity, so we are getting 0. So for example, now just taking the Z for the high temperature that is approaching infinity, so we have G naught e raised minus E naught over kT, and here is just energy is 0 plus G1 e raised minus E1 over kT, and so on. This is going in the same way, but just coming here that G naught e raised here if you put 0 over infinity, so from that we are getting 1, that is e raised 0 is equal to 1, and this is G naught. Just taking this degeneracy common because this is creating some problem from all, and here is e raised minus, and we are taking this term is, if this is a number 1 over infinity. So mathematically, if you have a number and if you are dividing any number by infinity, so you are getting a 0. So from this you will get a 0 value, this gives us 0 value. So here we also have from this term we also have e raised 0, we also have 1, and so on. This will go in the same, it will go. So we have Gi, and here from all this first term we already got 1, and from the second term 1, and from other one 1, and from the fourth one, and this is going on, and this is going to infinity. So this shows that if the temperature is approaching infinity, so Z limit temperature infinity, so the partition function will be infinity. That is all energy states, or virtually all energy states, will be equally probable for occupancy if we have temperature very high. That is, in other word, it means that at very high temperature all energy levels or energy states are equally probable for occupancy. That is, the particle can equally go into any energy level, that is, energy levels are very spacing or very close to each other. So this was all about introduction of the partition function. Okay, so now we are going to explain the vectorizability of partition function, that is total partition function, or in other words molecular partition function. So the total partition function or molecular partition function of all kinds of motion in the assembly of n particle is the sum of individual partition function that is contributed by different kinds of motions, that is translational motion, vibrational motion, rotational motion, electronic motion, or nuclear motion, because these kinds of motion they contribute particularly to the energy of the particles. So the total energy is contributed by these kinds of motion, and this will determine the total partition function. Now just taking the equation, main equation of partition function, and just putting the total value for the partition function, degeneracy and energy. So the degeneracy will be the product of different motion, and similarly the energy will be the sum of different kinds of motion contributed by different kinds of motion. Just putting the value in this basic equation, so we have the total partition function is product of degeneracy of different motions, summation e raised minus translation energy plus vibrational energy plus rotational energy plus electronic energy plus nuclear energy divided by whole divided by kT. Separating the terms, just simplifying, so we have this degeneracy for different kinds of motion, and just separating these terms for different kind of motion: translation, rotation, vibrational, rotational, etc. Similarly, just multiplying with the corresponding degeneracy, that is translational motion, vibrational motion, and this term is for rotational, and this is for electronic and nuclear, and so on. And just putting the value of just symbol for different kind of motion, that is the translation partition function is represented with zt, zv vibrational partition function, this is rotational partition function, and this is electronic partition function. So these are different kinds of motion which contribute to the total partition function, and thus the total partition function is the product of individual molecular motions. So this is some kind of about the partition function, total partition function. Now we are going to another interesting topic that is very important before explaining the different individual partition function, that is which include translational, vibrational, rotational, and for that we need to understand the degree of freedom, which is very important. You have already studied in physics or physical chemistry degree of freedom. So it's coming from three words, that is degree, and this is freedom. So freedom is particularly, you already know that how much freedom is available for a particle or any entity to move, and this degree is just showing the how intense or high or low this availability is present. We can define in simple word that the minimum number of independent variables, the degree of freedom can be defined as the minimum number of independent variables. So here is the word independent variables. Just keep in mind, we have to come to this word, this term again, and explain the independent variable required to fix the position and configuration of a dynamical system. So the position and configuration in dynamical system means a system which is always in motion, dynamic. Now we are coming here a very simple classical example of rolling ball or rolling stone. So on x-axis we shown the independent variable, and on y-axis we have shown just dependent variable. So this y variable depend on this x variable, but x variable is independent. So now the stone is, we are changing the x variable, the position with respect to this x-axis. So when we are changing the position with respect to this x-axis of this rolling stone, for example the rolling stone we are bringing here, so you can see we just change the position with respect to x-axis, but the y-axis is automatically changed, and as the stone is moving along and we are changing the position with respect to x-axis, that is independent variable, so the y-axis is automatically changed. If the stone is coming here, we change the position with respect to x-axis, so the y-axis is automatically changed, it is decrease according to this scale, and if the stone is coming here, so the y-axis is automatically going to 0. Now just going from a classical example of free particle, such as a mosquito is coming to this particular room. So we have this x-axis, that is x-axis, and this is just consider y-axis, and that is z-axis. So it has all possibility for movement, that is it can go along x-axis, along y-axis, it can go along z-axis. So it has all possibility, and that is represented by the three Cartesian coordinates, that is x, y, z. So but generally for n number of particles, the degree of freedom is represented as 3n formula. And if you have n number of particles with the n constraint, that is limits, so the total degree of freedom is represented with 3n minus k. So this is for the n number of particles with k limits. Now we are explaining this step by step, going from simple example to complicated one. For a particle to move on a two-dimensional surface. So now if we have a particle and that particle is free to move on a two-dimensional surface. For example, here this is a particle, and this particle is left to move on a two-dimensional surface. So what is the possibility? The particle can move either along x-axis, along y-axis, and the particle don't have possibility because it couldn't cross this board. So is the constraint, that is 1. So that is z is equal to 0 in this case. So 3 minus 1 is equal to 2. So these are two independent variables that can show the position of this particular particle, that is x-axis, either this is plus x-axis or that might be minus x-axis, that is right and left side. The particle can move from the origin, or this can move up and down from the origin, that is plus y-axis minus y-axis. So this can show us the position, either the particle is here, or in the positive coordinate or positive negative coordinate. So this, from this we can determine the position of this particular particle. Now if we have a particle that is moving, is compelled to move on a straight line. So for example, this is a particle, another particle, and this particle is compelled to move on a straight line. So this straight line might be x-axis or y-axis. So for this second particle to move on a straight line, so for this we have the y-axis and z-axis is 0, and that is constraint. We have two constraints, and the particle can only move along one axis. So this can move along one axis. So we have a degree of freedom for this particular case is 3 and 2 1 minus 2. So this is, we are getting 1. Now just coming towards a simple pendulum example. A simple pendulum, we hang a ball above through a string. So this is the length of this string is fixed, so that is a principal L, and this is moving along one axis. So what will be the total degree of freedom? Because this is 1, the particle is 1, and there are constraints. So what are those constraints which the particle couldn't move, and the particle has a freedom to move along those? So here this total degree of freedom is 3, and we have constraint 2. So what are those constraints? So those constraints are that because the particle, in this case this pendulum, the length of this pendulum is fixed, that is, it is fixed. And the second thing, that the pendulum only move along one axis. So these are the two constraints. So for that reason k is equal to, k value is equal to 2. And what is actually the independent variable that can give us the position? So that independent variable is the angle, and that angle is with respect to the normal. So from this we can see that if the angle is 30 degrees, so we can take a different position. If the angle is a little higher, that is 45 degree, so we can see that it is at a different position. So from that we can determine its position. So this was the case with the simple pendulum. But now if we have another case in which we have a double pendulum. So in case of a double pendulum, we have a single pendulum, same case, and we attach another pendulum here. So when the pendulum is moving, a single pendulum is moving along x-axis, the other pendulum is also moving along x-axis. So in this case, what will be the total degree of freedom? In this particular case, the total degree of freedom is 6. But what will be the constraint for these two kind of pendulums, because these are two bodies right now, 1 and 2. So for that the constraint are the same, because the length of this pendulum is fixed, also this pendulum is fixed, and this pendulum is moving along the same axis, and this one is also moving along the same axis. So we have two constraints for one pendulum, 2 for another, so we have total 4. So the constraint are 4, and we have the total degree of freedom 2. So from the angle of this pendulum we can see the position, we can determine the position, and from this we can also from this independent variable, that is angle, we can determine the position of the second pendulum. Hope that clarify your concept. If you have any question, then please don't hesitate to ask. Later on we will go to from classical example to molecular example.